Hello physics students, Mr. Dillick here again, and this is going to be videos 7 and 8 combined together, and it's about kinematics. We've been talking about acceleration in the last couple of videos, and in the last video we took a time out to talk about the acceleration of something that's moving in a circular path, but really we don't really want to talk about multidimensional motion just yet. Let's get back to talking about things that are moving linearly and yet they're accelerating. You may recall that one time I mentioned that accelerations always go with forces. Things speed up and slow down and change direction because they're experiencing a force that's pulling on them or pushing on them in a certain direction. And if that force is really constant, it's going to produce what we call a constant acceleration. So constant forces cause constant acceleration. So we mean constant in magnitude, how much oomph somebody's putting into that push or pull, and constant in direction, because acceleration is a vector, and as it turns out, force is a vector as well. So there's a whole branch of physics that describes objects that are experiencing this constant acceleration, and that's a branch of physics called kinematics. And I want you to get pretty good at identifying whether or not a motion is kinematic or not. Again, we're talking about things that are experiencing constant acceleration. So a lot of times the best example of a force that's a constant force that produces a constant acceleration is gravity. It's constantly pushing down on us, so the direction isn't changing, and it's constantly pulling with the same magnitude. So if something is experiencing a constant acceleration, there are several equations that we can use called the kinematic equations to describe the motion. But we have to be really sure that in order to use those equations, we have to be really sure that the object meets two conditions. And one of the conditions is that the object definitely has to be experiencing a constant acceleration. So there has to be a constant force pushing or pulling on it. And gravity will always count as a kinematic force. But in addition to that, it has to cause the object to move in a straight line. And so we want to make sure that you know that this goes for things that are experiencing a constant acceleration in a straight line. So a really good example would be an object falling straight down. An object that was falling straight down is experiencing a constant force of gravity and it's moving in a straight line. So it would be considered an example of a kinematic motion. Now, when objects move that way, they're going to produce pretty specific graphs, and I want to show you what those graphs look like so that you have a really good idea of when you're looking at a graph if it's a kinematic motion or not. So let's talk about what those graphs would look like if it was kinematic. Okay, so what I have here for you are an example of an acceleration and a velocity, an acceleration time graph, a velocity time graph, and a position time graph for something that is experiencing an acceleration that's constant, but the object's moving in a straight line. Now, this could be anything. It could be gravity, but, since we went with x down here, it doesn't have to be gravity. It's just something that's experiencing a constant negative acceleration. So there's something constantly pushing or pulling this object in a negative direction. And if it happens to be x, it's constantly pulling or pushing it to the left. If it happens to be a y direction, then we're just constantly pushing it down. And if it's z, it's constantly pulling or pushing it backward. Either way, what we see is that when we have constant acceleration, we're going to have a horizontal line that's not at zero. If you see a horizontal line that's not zero, then you have a constant acceleration, and that's a kinematic graph. That's going to cause something to have a slope that's constantly negative. So if you see a line with slope, basically any velocity time graph that doesn't have a horizontal line, but does have a line and not a curve, is definitely going to be kinematic. So we see that it's experiencing a line with slope. And it doesn't matter if that started out moving in the positive direction, stopped, and now is moving in the negative direction, or if it started out at rest and is now constantly moving in the negative direction, or if it started out moving in the negative direction. It's moving in a constant negative direction, but it's getting faster the whole time. Any of those, if we shift this up and down, any of those would all be kinematic, as long as the line has a constant slope. As long as there's a line, it's going to have, by definition, a constant slope, as long as it's not a horizontal line. Meanwhile, I should mention, it doesn't matter if this is a positive acceleration or it's a negative acceleration, it just can't be that. It can't be zero. And then What about the position time graph? What will that look like? Well, remember we said forces cause accelerations, and accelerations on position time graphs are curves. So basically, you see parabolas. I don't care if they're upward opening parabolas or downward opening parabolas like this one, or even a rightward opening parabola. If we see parabolas, then we know we're talking about something that has an acceleration, because curves on position time graphs mean acceleration. Now, why do we care about this? Well, a lot of times when you're looking at a position time graph, it's really easy to answer questions about what the displacement of an object is. But what if you're looking at a velocity time graph? Can we figure out displacement, or actually anything at all about position, when we're looking at a velocity time graph? And the answer is, well, yes and no. We can never find out about instantaneous position without additional information. But could we get a kind of total change in position? Could we figure out displacement? Yes, we can. And here's what I mean. Okay, so these are both velocity time graphs. I only labeled the first one, but both this blue one and the red one are both velocity time graphs. And imagine I wanted to know what the displacement was for this object. Well, if you think about this object starts with an initial velocity of 10. It stays at a constant velocity of 10. So is this kinematic? No. This is a velocity time graph that doesn't have slope. It has a horizontal line. So it's not considered kinematic. And that's going to matter. Because if I asked you how far does this object go in the first 10 seconds, what's its displacement, you could actually figure that out with some basic geometry. We know that it's traveling at 10 meters per second for 10 seconds. So with just a basic equation, velocity is displacement over time, we can kind of rearrange that and say, well, displacement is velocity times time. So you take 10 meters per second and you multiply it by 10 seconds, we can kind of see that this object is traveling 100 meters in those 10 seconds. Well, how did we do that? Well, if you think about it, what we actually did was we actually found the area of this rectangle right here. So you can see the velocity that it traveled at the entire time on average was 10 meters per second in the positive direction. It did that for 10 seconds. So if you take the definition of average velocity as being a displacement over time, and you just kind of rearrange it algebraically, you can see that the 10 meters per second times the 10 seconds gives you the 100 meters, which is the area of this rectangle under the line from 0 to 10. And so what we can say about that is the area under this curve, the area under this line, tells us the displacement. And so the area of a rectangle is base times height. It's 10 times 10. Now that's easy to do if you're talking about something that's non-kinematic like this, but what about something like this where part of it is kinematic? Sure, the last 5 seconds here, it's not a kinematic motion, but for the first 5 seconds, it is. If we wanted to know the displacement here, we'd have to add up a significantly more complicated area. We'd have to find the area of this triangle and add it to the area of this rectangle, and together we would get our displacements. We'd have to do the area of a triangle, we'd have to do base times height and divide it in half. After all, it's half this square. And then we'd have to add it to the base times the height of this. And so that would look like this. So here you can see we're doing the same thing. We've got a smaller rectangle here because it's only for 5 seconds. So we can see the base of this is 5, the height of this is 10. So 15 meters is how far it travels during this time. Then, if this wasn't a triangle, if this was just all the way across, we know that this would be 50 and this would be 50. But this is actually half of that square or that rectangle. And so you take half of that 50, add it together. So we can see that it's only traveling 75 meters here where it travels 100 meters during the 10 seconds. So what does that mean to us? Well, it means that we can find the area under the curve to find displacement. And that's useful, but it's kind of a pain in the butt. Because this whole doing geometry and adding that up is kind of hard. Is there an easier way to do that with math, right? So that we don't have to do this whole geometry thing? And the answer is yeah, as it turns out there is. If we could find the same information using math, that would be great. And so we have a whole set of equations that we can use to do that called the kinematic equations. So let me tell you a little bit more about them. So there are actually 4 kinematic equations. These 4 equations can only be used if we know something's moving in a straight line under constant acceleration, and they look like this. Okay, so these are the 4 kinematic equations, and they look really scary, but they're not actually that scary. Once you get the hang of what to do with them, they're actually really great because they make the job of finding the area under the curve quite a bit easier. And these aren't necessarily in the order you find them in your book, but the first one says delta x displacement is 1/2 times the quantity v initial plus v final times time. And if you're taking something's initial velocity and final velocity and adding it together and dividing it in half, that's basically average velocity. So this basically says displacement is average velocity times time. We've known that for a while. This one says final velocity equals initial velocity plus acceleration times time. This one says final velocity squared equals initial velocity plus 2 times acceleration times displacement. And this one says displacement equals initial velocity times time plus 1/2 times acceleration times time squared. So my A's sometimes look a little bit like 2's. I hope that doesn't throw you off. All right, so what are these equations for? Well, each of these equations contains what are called the 5 golden variables. And the 5 golden variables are acceleration, which is linear and constant, because we already said you can't even use these unless we know that the object is moving in a straight line with a constant acceleration. Initial velocity, which is how fast the object is going at the moment we start paying attention to it. Final velocity, which is how fast the object is going instantaneously at the moment we stop paying attention to it. Time, which is whatever duration of time we're watching it, and then displacement. And I just chose x here because that's the standard, default. But it could be delta y or delta z if it's in a different direction. This is displacement, or a change in linear position along whatever number line we've indicated with our letter there. Now, I have given these equations informal names, and the names are really important because the names tell you how to use the equation. So let me rewrite these equations with a pretty important piece of information. Although there are 5 golden variables, each equation has only 4 of those variables in it. There's one variable that's missing, and the missing variable gives it its name. Let me show you. Okay, so again, the golden variables are acceleration, initial velocity, final velocity, time, and displacement. In this equation right here, we have displacement, initial velocity, final velocity, and time, but no mention is made of acceleration. So I informally call this one the no acceleration equation. This one has final velocity, initial velocity, acceleration, and time, but is missing displacement. So I call this one the no displacement equation. This one has displacement, initial velocity, time, acceleration, and time again. So this one is missing final velocity. I call this one the no final velocity equation. And finally, this one is final velocity, initial velocity, acceleration, displacement, but has no mention of time. So I call this the no time equation. Please notice that there isn't an equation that's missing initial velocity. They all have initial velocity in them. So the initial velocity is a pretty important variable that you need to know to use these equations. You're pretty much either always going to be solving for it or have it. On the other hand, these ones are missing one of the variables, and the fact that it's missing that variable really helps you figure out how to use the equation. For instance, what that means is if you're given an equation and if you're given a problem and that problem, no mention is made of acceleration, you're going to use the no acceleration equation. Let me show you. Let's say that we have a plane, and that plane is taking off. And you're told that the plane is taking off with an initial velocity of 0. It's starting from rest. It's going to speed up to a final velocity of 100 meters per second. It's going to take about 50 seconds to do that, and it's going to be something that you want to figure out how long that runway is. Well, what were you given? What we're doing is we're using the guess method. G for givens, list your givens, U for unknown, E for equation, S for substitution, and the other S stands for solve. So you're given that it's starting at rest. It's going to get up to a speed of 150 meters per second in 50 seconds, and we want to know, our unknown is, what's its displacement? Notice, we've mentioned 4 of the 5 variables. Which variable was no mention made of? That would be acceleration, so that means we're going to use the no acceleration equation. And that one happens to say delta x equals 1/2 times the quantity v initial plus v final times delta t. It doesn't matter what order you have these in, because when you add them, it just doesn't matter. So if I plug in the numbers, I get 3,750 meters. That's going to cover about 37 football fields during that time. So all of them work this way. I'm going to go back one slide here. If you are given, for instance, acceleration and velocity initial and velocity final, and you're solving for displacement, you can use the no time equation because no mention is made of time. But if you were given initial velocity, final velocity, acceleration, displacement, and you were solving for acceleration, you could also use the no time equation. If you know any three, you can find a fourth. It doesn't matter what three. Good luck.